Somewhere, maybe a million years ago, maybe longer, maybe not quite that long, someone held a piece of meat near a flame. Maybe they dropped it by accident. Maybe they were curious. Maybe they were just cold and hungry and desperate enough to try something new. And whatever happened in that moment, whatever that first cautious bite tasted like, it changed everything. Not immediately, not in a way anyone noticed, but slowly, over thousands of generations, that small act, food meeting fire, began reshaping the human body, the human brain, and eventually human civilization itself. Tonight, we're going back to that fire. If you're using this to fall asleep, that is exactly why I make it. So subscribe if you haven't, and drop a comment telling me where you are right now and what time it is. I genuinely read them. It's Sydney at sunrise, Sao Paulo at midnight, Stockholm at 3 in the morning. All at once, that never stops being strange and kind of wonderful. Get comfortable, because we're going a long way back. We're talking about deep time, the kind of time that makes recorded history feel like the last 5 seconds of a very long movie. We're talking about early humans barely recognizable as us, crouching around fires they may or may not have fully understood, in landscapes that no longer exist, eating food we'd probably find unrecognizable. And yet, if the evidence is right, something that happened around those ancient flames is the reason you are the kind of creature who can lie here tonight, thinking about any of this at all. Here's the central question this episode is built around. When did humans actually start cooking? Not just using fire occasionally, not just warming themselves near a burning tree struck by lightning, but deliberately, consistently applying heat to food as a technology. And how do we even know? The evidence is fragmentary. Fire doesn't fossilize cleanly. Ancient hearths can be destroyed, misidentified, or misread entirely. Scientists debate the dates constantly, so we won't be handing you certainties tonight. What we'll do is walk through the best supported possibilities, the clues archaeologists have pulled from ancient sediment and bone and ash, and let the evidence speak for itself, incomplete as it is. And then there's the deeper question, the one that makes this more than just an archaeology story. Did cooking actually make us human? Not metaphorically, literally. Did the act of applying heat to food unlock enough extra calories to fuel a larger brain? Did it free up enough time and biological energy that our bodies began to change, jaws shrinking, guts shortening, skulls expanding? This is what scientists call the cooking hypothesis, and it's one of the most compelling and contested ideas in all of human evolutionary science. We'll spend real time with it tonight, exploring what it gets right, where it runs into trouble, and why even its critics think fire was probably one of the most important technologies our ancestors ever touched. We'll also go beyond the biology, because fire didn't just change what early humans ate. It changed when they were awake, how they related to each other, what dangers they could survive, and possibly what stories they first began to tell. The hearth is one of the oldest social technologies in existence. Long before cities, long before agriculture, long before writing, there was a circle of people around a fire, sharing warmth and food, and probably something that looked a lot like conversation. But before we get to any of that, we have to start with the hardest part of the whole story, finding the actual evidence. Because the first question any honest scientist has to answer is this: how do you find a fire that burned 1 million years ago? How do you distinguish a campfire from a lightning strike, a deliberate hearth from a natural burn? What does ancient cooking actually leave behind? That's where the story gets genuinely fascinating, and a little humbling, because the traces are fainter than you might expect, and the debates are fiercer than most people realize. Before we can talk about cooking, we have to agree on what cooking actually is. Because the word gets used loosely, and in evolutionary science, looseness costs you. Cooking, in the sense that matters here, means intentional heat transformation, deliberately applying fire or hot surfaces to food in order to change it. That's the definition that draws the meaningful line. It's different from drying meat in the sun, which removes moisture but doesn't fundamentally restructure the food's chemistry. It's different from fermentation, which uses microorganisms rather than heat to break down cellular structures. It's even different from leaving food near a fire for warmth versus actually putting it in the flame. The distinction is intentionality combined with heat, and the reason that line matters is because crossing it requires a specific kind of cognition. You have to understand, even dimly, that heat will do something useful to this thing you're holding. That's not a trivial leap. We'll come back to how and when our ancestors might have made it. But first, we need to understand what life looked like before that leap. What it actually meant to be a raw-eating ape. Start with your closest living relatives. Chimpanzees spend somewhere between 4 and 7 hours every single day just chewing. Not foraging, not travelling, not socializing, just working food through their mouths. Their jaws are enormous relative to their skull size, their molars wide and flat, their jaw muscles so powerful they anchor to the top of the skull through a bony ridge called a sagittal crest. All of that anatomical machinery exists for one purpose: processing raw plant material which is fibrous, tough, and remarkably resistant to digestion without serious mechanical preparation first. Gorillas have it even harder. A lowland gorilla might spend close to half of every waking hour eating. Not because they lack access to food, but because the food they have access to demands that much time to extract enough usable energy from it. Raw leaves, raw stems, raw fruits that aren't quite ripe. Every calorie is hard-won through effort and time. This is the baseline. This is what the primate body plan is optimized for when heat is not part of the equation. And it's a genuinely constrained way to live. Time spent chewing is time not spent doing anything else. Finding mates, watching for predators, exploring new territory, learning new skills, caring for offspring. Every hour locked into the mechanics of raw food processing is an hour unavailable for the things that might, over evolutionary time, provide an advantage. Now consider the caloric economics more carefully. Raw food, even high-quality raw food, is not fully available to the digestive system. Plant cells have walls made of cellulose, which mammalian digestive enzymes can't break down efficiently. Meat eaten raw is harder to denature, meaning the proteins are folded in ways that make them less accessible to stomach acids and intestinal enzymes. Starchy tubers and roots, which would have been a major food source for early humans on open African landscapes, are difficult to digest in their unaltered state. The starch granules are tightly packed and partially resistant to the amylase enzymes in saliva and the small intestine. So you eat a raw tuber, and your body extracts maybe 60 or 70% of what's theoretically in there. The rest passes through. Raw food also comes with risks that we tend not to think about anymore. Pathogens, bacteria, parasites, and other microorganisms that thrive in uncooked animal tissue. A kill on an African savanna in the middle of the dry season, left exposed to heat, for even a few hours begins to harbour bacterial populations that can cause serious illness or death. For a small group of early humans living far from any kind of medical help, a bad piece of raw meat wasn't just unpleasant, it was potentially catastrophic. And then there's the question of toxins. Many plants produce chemical defences, compounds designed specifically to deter the animals that might eat them. Some of these are neutralized by heat. Others accumulate to dangerous levels when consumed raw in large quantities. An animal that could render those defences harmless through cooking would have access to an enormously wider range of plant foods. That breadth of access, especially during seasons when preferred foods were scarce, could make the difference between surviving a drought and not surviving one. All of this points toward a single underlying reality. A raw diet for a primate with any ambition toward a larger brain or a more complex social life is a treadmill. You spend enormous time and energy just staying even. The energetic math is unforgiving. Bigger brains are metabolically expensive. Human brains today consume roughly 20% of our total caloric budget, while representing only about 2% of body mass. That's a wildly disproportionate energy demand. A brain that size, running on a raw diet, would require either dramatically more foraging time or dramatic reduction in energy spent elsewhere in the body. Probably both, and there are hard limits on how far either strategy can take you. This is what evolutionary biologists sometimes call the energetic trade-off problem. Every calorie your body diverts to one system is a calorie not available to another. Long gut, big brain. You generally can't maximize both. The digestive system of a primate eating raw food is long, muscular, and energetically expensive to run. It has to be. It's doing a lot of heavy lifting to extract nutrition from materials the food hasn't already been broken down for it. The human gut, by comparison, is notably shorter and simpler than you'd predict for a primate our size. Something reduced it. Something changed the equation. The cooking hypothesis, which we'll dig into properly in a later section, suggests that heat did that. That once early humans began consistently applying fire to food, they were effectively outsourcing some of the digestive workload to the flame, pre-digesting their food before it ever entered their bodies. And that freed up enough energy to fuel something unprecedented. But here's the thing worth sitting with for a moment. We don't know exactly what pushed our ancestors toward that threshold in the first place. Raw food is a constraint, yes, but it's a constraint that worked well enough for millions of years of primate evolution. Australopithecines, the hominin ancestors, who walked upright but still had relatively small brains, managed on raw diets for a very long time. So the question isn't just whether cooking is better, it's what changed. What pressure or opportunity moved our lineage toward fire as a food technology rather than simply continuing to manage on raw resources the way every other primate did? Some researchers think the answer lies in environmental shifts, in the expansion of African grasslands that reduced the availability of easily digestible fruits and forced hominins increasingly toward harder-to-process foods like tubers and meat. Others point to social dynamics, to the possibility that a group which could share cooked food gained cohesion advantages over groups that couldn't. Some think the initial nudge was accidental. Food falling into fires started by lightning, early humans tasting the result and finding it preferable, then slowly, haltingly, beginning to seek out that result deliberately. None of these explanations are mutually exclusive. Evolution doesn't usually work through single causes. It works through pressures that overlap and compound, through accidents that become habits, and habits that become biology. What we can say is that somewhere in the long stretch of hominin history, the balance shifted. The costs of raw food began to outweigh the effort of managing fire. And when that happened, when the flame became a tool, rather than just a hazard or a curiosity, it set in motion a chain of biological and social changes that eventually produced something genuinely new in the history of life on this planet. But to understand when that happened, and how we could possibly know, we have to go looking for the evidence. We have to ask what a million-year-old fire actually leaves behind in the ground. What archaeologists dig up when they're trying to find the moment heat became part of the human story. Because the traces are there, they're subtle, they're contested, and they're remarkable. And they're exactly where we're going next. When archaeologists go hunting for the first human fires, they're not looking for dramatic blackened camp circles the way you see in movies. 1 million years is a long time. Ash blows away, wood disappears. Bones dissolve, landscapes erode, flood, crack, and fold. What's left, if anything, are whispers. Those whispers come in a few basic dialects. One is ash, not fluffy grey fireplace ash, but what specialists call ash lenses. Thin, pale layers tucked into the soil, sometimes only a few millimetres thick. Under a microscope, those layers can show the ghostly outlines of burned plant tissue, the cellular structure warped and collapsed by high heat. If the ash is concentrated in a tight patch, especially with other traces stacked above and below, that starts to look like a place where fire was made, not just where lightning struck once and moved on. Another is charcoal. Charcoal is sturdier than ash, more likely to survive burial, tiny black fragments, sometimes only visible when you float soil in water or sieve it carefully. Under magnification you can still see the wood's growth rings, its pores and vessels, but they're glassy, glossy, transformed. Charcoal tells you that something organic burned hot enough and quickly enough to carbonize rather than rot. That could be a forest fire. It could also be your ancestors tending a hearth. Then there's burnt bone. When bone meets fire, it doesn't just darken. It changes colour and texture in stages. At lower temperatures it turns brown, then black, as the organic collagen burns off. With sustained higher heat, it goes blue-grey or chalky white, the mineral matrix recrystallizing, the bone warping or cracking in distinctive patterns. If you find a cluster of bones like that, mixed with stone tools and ash, the story starts to write itself. Someone brought an animal here, butchered it, and some of that tissue met fire. Even the dirt remembers. Sediments exposed to repeated heating can turn reddish or orange as iron minerals oxidize. Clay near a hearth can harden, almost like primitive brick. In cross-section, archaeologists sometimes see a reddish halo beneath or around a suspected fire patch, a stain left by years of low, steady heat soaking into the ground. And rarely there are hearth structures, rings of stones or shallow scoops in the earth lined with rocks, with ash and charcoal pooled in the depression. These are late in the story compared to the very first fires, but they're important because they show what a fully developed fire feature looks like. Once you know the clear version, you can start to recognize fainter, earlier cousins. None of this is simple. The Earth is not an archive designed for our convenience. The older you go, the worse the preservation gets. Wind and water shear off entire landscapes. Rivers meander and cut away ancient banks. Earthquakes tilt layers, volcanic ash buries sites, and then itself erodes. Later, humans dig holes, build shelters, make their own fires on top of older ones, mixing traces together. On top of that, nature burns too. Lightning starts wildfires. Volcanoes set hillsides alight. Natural bushfires can leave charcoal lenses and reddened soils that look, at first glance, suspiciously human. If an ancient lake margin caught fire thousands of years before any hominin walked past, its burned sediments might still be there, waiting to fool someone who wants an early date for human fire a little too badly. So archaeologists have had to become fire detectives, developing methods that go beyond this looks sort of blackened. One tool is microscopy. Thin slices of sediment are set in resin, polished, and examined under powerful lenses. At that scale, you can tell the difference between ash that formed in place and ash that washed in later. You can see whether charcoal pieces are angular and fresh broken or rounded from tumbling in water. You can identify burned plant species even by their anatomical patterns. All of this helps sort hearth debris from random fire leftovers. Another line of evidence comes from physics. When soils and stones are heated above certain thresholds, their magnetic properties change. Tiny iron-rich grains inside them can realign with the Earth's magnetic field as they cool, essentially recording that they were once hot. By measuring these magnetic signatures, scientists can sometimes show that a patch of sediment was heated to several hundred degrees and then stayed put. That's more like a hearth than a passing grass fire. Minerals tell their own version. Quartz and flint can develop new crystal structures when heated. Clays can dehydrate and reconfigure. Under laboratory analysis, you can spot these transformations and estimate minimum temperatures. If bones show patterns consistent with controlled, moderate fires rather than brief scorching, that points towards someone tending the flames. And context is everything. Burned materials scattered randomly through a thick layer might be the residue of repeated natural fires over centuries. Burned materials tightly clustered with tools, cut-marked bones, and other traces of human activity in a spot that recurs layer after layer in the same place. That begins to look like a habitual fire spot. Even then, archaeologists are careful about the words they use. There's a big difference between fire use, fire control, and habitual cooking. Fire use can be as simple as scavenging warmth from a natural blaze, or grabbing a partially burned log from a lightning-struck tree to scare off predators or singe some food. Fire control means more, the ability to keep a flame going, to tend it, to move it, perhaps even to rekindle it when it dies. Habitual cooking is another leap again. That's fire being used deliberately again and again, specifically to transform food, not just once, not just opportunistically, but as part of daily life. In the dirt, those distinctions blur. A single ash lens might mark a one-off use of lightning fire, or a briefly maintained hearth. A long sequence of stacked, similar lenses in the same spot, associated with food remains, looks more like regular controlled use. But proving cooking rather than simply fire is notoriously challenging, especially deep in time. Timing is another tangle. To know when a fire burned, you have to date the layer that contains its traces. The most basic method is stratigraphy, reading the sequence of layers, with the understanding that, all else being equal, deeper usually means older. If a hearth is sealed beneath a layer of volcanic ash that can be dated radiometrically, that gives a maximum age. If charcoal survived and is recent enough, radiocarbon dating can estimate when the tree it came from stopped taking in carbon. For really old sites, other radiometric techniques come in, methods that measure trapped electrons in heated flint or minerals, or the decay of radioactive isotopes in sediments. Each method has its range and its weaknesses. Charcoal can be redeposited from older layers, making a fire seem older than it is. Burrowing animals and plant roots can drag younger material downward, making things seem younger. Erosion can erase parts of the story altogether, leaving an isolated patch that's hard to place in the proper sequence. This is why caves and lakeshores loom so large in discussions of early fire. Caves are natural shelters from wind and rain. They collect and preserve layer upon layer of occupation debris. Ash and charcoal dropped on a cave floor are more likely to be buried gently rather than scattered by storms. Lake shores and river margins, similarly, build up fine sediments that can entomb fragile traces. But both settings can mislead. Caves act like funnels, pulling in materials from outside. A wildfire on the hillside above can wash charcoal inside, sprinkling it into layers where no one ever lit a deliberate flame. Lakeshores flood, reworking old sediments and depositing them in new places. A hearth might be eroded away entirely, leaving behind only faint traces mixed with natural burning products. So when archaeologists argue about the earliest fire, they're often arguing about these fine-grained details. Is the ash in place or washed in? Are the bones burned where they lie, or did they tumble down from somewhere else? Do the mineral and magnetic signatures really demand controlled, concentrated heat, or are they compatible with a natural burn? Despite all this uncertainty, a few sites keep coming up. Places in Africa, in Israel, in Europe, where multiple lines of evidence converge just enough to make people wonder if we're looking at the first shadows of tamed flame. They're not smoking guns. They're more like embers buried deep in geological time. In the next section, we'll visit some of those candidate sites, move layer by layer through their evidence, and see what they suggest about when our ancestors first began to reach for fire, and what they might have done with it when they did. If you follow those embers back through time, you eventually run into a wall of maybe. One of the oldest maybes comes from around 1.5 million years ago in East Africa. Places like Kubifora and Chezawanja in Kenya have produced patches of reddened sediment, bits of stone that seem heat-altered, and scattered charcoal. For a long time, these were held up as the earliest signs of controlled fire. Under the microscope, some of those materials really do look burned. The minerals have changed in ways that fit high temperatures. A few pieces of stone appear to have been heated and then knapped, as if someone struck tools off them after they had been near a flame. But the context is messy. The burnt pieces aren't neatly clustered with clear traces of camp life. The layers have been jostled by water and erosion. Some researchers see these as promising hints of human-tended fire. Others argue they're just the fingerprints of natural grass fires that swept across an open landscape where hominins also happen to be living. So Kubifora and Chezawanja have slid, over the decades, from earliest hearths in textbooks to something softer, possible early fire use in a landscape where natural burning was common. A similar debate surrounds Swartkrans Cave in South Africa, with deposits roughly 1 million years old. Here, archaeologists found bones that had been heated to temperatures compatible with controlled fire, along with stone tools and hominin fossils. The optimism was understandable. Burned bone, tools, hominins, all together in a cave. That sounds like a recipe. But again, details complicate the story. Were those bones burned in the cave or outside in natural fires and later dragged in by carnivores? Some studies claim the temperatures and colour changes fit sustained hearth fires. Others say the pattern could just as well come from a brush fire that roasted carcasses on the surface before they were scavenged. Swartkrans has settled into that ambiguous middle category. Probable human association with fire, but not universally accepted as evidence of regular, deliberate burning, let alone cooking. To sort these cases, archaeologists lean on a few key questions. First, location. Is the burning where humans were definitely living? In an open savanna, natural fires can sweep across for miles, leaving charcoal and burned soil almost everywhere. In a cave interior deep away from the entrance, fire is less likely to wander in on its own. So red, heated sediments far back in a cave, layered with tools and bones, are more suspicious in a good way than scattered charcoal on an exposed hillside. Second, pattern. Natural wildfires tend to produce broad, uneven swaths of burning. Human fires often leave tight clusters. Repeated use can stack those clusters into vertical sequences, ash lens on top of ash lens, all in the same small spot. If burnt materials are tightly grouped, if they reappear in the same few meters over and over, that smells more like people reusing a favourite hearth location. Third, association. Are the burned things mixed with unmistakable traces of human behaviour? Stone tools that clearly show napping marks, bones with cut marks from stone blades suggesting butchery, broken bones split in ways that fit marrow extraction. When burned bone, ash and such tools lie together in a coherent little package, the case for human-controlled fire strengthens. Finally, intensity. Some natural fires are incredibly hot, but many are quick, passing blazes. Human hearths tend to produce moderate, sustained heat in a confined area. Mineral changes in stones, the particular cracking patterns in bones, and those magnetic signatures in sediment can point toward either intense but brief burning or lower, steadier heating over time. Put all of these together and you get a spectrum of confidence. At one end are sites like Kubifora and Chesawanja, burning in environments where lightning fires were common, with limited clustering and weak association with clear activity areas. These are plausible early encounters with fire. Our ancestors may have warmed themselves there or grabbed partially burned branches. But the line between natural and human fire is blurry. In the middle sit places like Swartkrans and a handful of other caves, around 1,000,000 to 800,000 years old. Here, the evidence is stronger: burned bones, altered stones, cave settings that suggest at least some intentional use. Many researchers would say humans were probably interacting with fire at these sites, though how regularly and for what remains unclear. Then, around 790,000 to 780,000 years ago, we reach one of the most talked about sites, Gesher Beno Yaakov, on the banks of an ancient lake in what is now northern Israel. Here the pattern sharpens. Archaeologists have found clusters of burned flint, charred plant remains, and heated stones in distinct spots alongside stone tools and animal bones. Some of the plant remains look like nuts and seeds that would have benefited from roasting. There appear to be multiple discrete fire spots within the same occupation surfaces, suggesting repeated use of fire in different activity areas. Many specialists consider Gesher Beno Yaakov one of the earliest widely accepted examples of habitual fire use outside Africa. Not everyone agrees on every detail. There are still arguments about exactly how to interpret some of the burning, but the convergence of location, pattern, association, and intensity has pushed it toward the probable controlled fire end of the spectrum. Does that mean people were definitely cooking there? Possibly. The association with edible plant remains is suggestive. Roasting nuts or tubers would have made them easier to chew and digest. Lightly charred animal bones might point to meat being exposed to heat. But even at Gesher, caution is the rule. Cooking is a specific behavior, applying heat to food on purpose. Fire can char food accidentally as carcasses are butchered near a hearth, or as scraps are tossed into the flames. The archaeological record can rarely tell us whether those burned remains were culinary masterpieces or just sloppy waste disposal. And whatever was happening at that lakeshore, it probably wasn't yet the sort of constant, taken-for-granted cooking that defined later humans. Fire might have been a powerful tool, but still a fragile one, kept going when possible, lost when conditions were bad, perhaps rekindled from natural sources rather than reliably sparked from scratch. One of the striking things when you trace these sites through the literature is how interpretations shift over time. A discovery is made, the first analyses come out, and headlines proclaim the earliest hearth or first evidence of cooking. A decade later, new methods are applied. Sediments get resampled. Magnetic studies improve. Dating techniques are refined. Sometimes the age of a layer moves by 100,000 years in one direction or another. Sometimes what looked like a single hearth turns out, under finer analysis, to be a smear of fire debris reworked by floods. Occasionally, skepticism softens. A site that once seemed marginal gains support as independent teams confirm its signals. The language used in papers and books reflects this caution. Sites are described as possible, probable, or widely accepted examples of fire use. Control is reserved for cases where repeated, localized burning is hard to explain any other way. Cooking is used sparingly for the deep past, often hedged with phrases like may indicate, or is consistent with. What emerges across all the arguments is a gradual brightening rather than a sudden switch. Early hominins almost certainly knew what fire was. They lived in landscapes that burned seasonally. At first they may have only approached wildfires, scavenging cooked carcasses or warm coals. Later, they likely learned to nurture those coals, to keep them alive overnight or across days. Only much later still did fire become something more like a daily companion, a presence you could count on, a technology woven into the rhythm of gathering, hunting, resting, and crucially, eating. In the next section, we'll follow that shift from occasional, precarious flame to regular hearths. We'll look at the first clear fireplaces that show up again and again in the same spots, layered like pages in a book, and ask when tending embers turned into a routine part of being human. Somewhere between those scattered fire spots and the later, unmistakable hearths, a quiet revolution unfolded. It began with a simple shift in attitude, from fire is something that happens to the landscape, to fire is something we try to keep. Early on, our ancestors didn't know how to make fire. There's no evidence this far back for deliberate ignition. No clear signs of bow drills, fire ploughs, or the striking of specific stones to shower sparks onto tinder. Lightning, volcanism, and spontaneous brush fires were the real fire starters. People were, at best, fire catchers. Imagine a storm rolling over a dry savanna, lightning lancing into grasses, a line of flame racing along a hillside. Long after the main blaze raced past, patches of smouldering wood and half-burned trees would have lingered. For a clever, risk-tolerant hominin, those glowing logs were an opportunity. You didn't have to invent fire from nothing. You only had to be brave enough and smart enough to approach the edge of a burned patch, pick up a smoking branch and carry it away before it died, or before you got burned, or before the wind shifted and trapped you. At first that might have been the entire technology, scavenging heat from the sky's temper tantrums. But captured fire is fragile. A single gust, a sudden rain, a careless step, and it's gone. If you live in a world where you don't know how to spark a new flame, losing your coals is like losing access to metal or electricity today. Except worse, because you have no backup plan. You're back to waiting for the next storm. So the real change wasn't just picking up fire, it was learning how not to lose it. This is where hearths start to matter. A hearth is more than a burnt patch on the ground. It's a deliberately chosen spot where fire is expected to live. A shallow basin scraped into the floor of a cave, a ring of stones or a circle of packed earth on an open bank. A place that hosts flame today, tomorrow, and next season. With a hearth, fire becomes predictable. You know where the heat will be, where to gather when the sun drops, where to bring food that might benefit from smoke and warmth. Instead of flames wandering across the landscape, they are anchored, a fixed point in a moving world. That anchoring changes three things at once. First, reliability. If you tend coals carefully, you don't need lightning every week. You can rake embers together in the evening, cover them with ash to insulate them, and coax them back into flame in the morning with dry grass and breath. Over time, groups may have kept a lineage of fire going for weeks, months, maybe longer. A living thread carried from site to site, from generation to generation. Second, safety. A free-burning log can roll, tumble, spark into dry brush. A hearth puts boundaries around chaos. A shallow pit limits where embers can travel. Stone or damp earth edges reduce the chance of runaway flames. Sitting around a contained fire is very different from hovering at the margins of a wildfire. Third, repeatable heat. Human bodies and foods begin to experience fire as something with a pattern. You learn how close you can sit without scorching your skin, wherein the hearth meat sears fast and where roots can be tucked into cooler ash, where smoke flows when the wind shifts. Heat is no longer an accident. It becomes a resource with gradients you can exploit. To make that possible, daily life has to bend itself around fuel. Once you have a hearth to feed, you need wood, dung, grasses, or whatever will burn. Gathering those materials is not just extra work, it's a new way of paying attention to the landscape. People learn which woods burn hot and fast, perfect for a quick blaze at dusk, and which burn slowly and steadily through the night. Dense hardwood that turns to long-lasting coals, resinous branches that flare bright but vanish quickly, twigs and bark that catch sparks easily, rotten logs that produce more smoke than flame. These preferences carve invisible paths into the environment. Children trail adults as they walk the same loops day after day, eyes automatically scanning for dead branches, driftwood, dried shrubs. They start to build mental maps. That gully always has fallen limbs after a storm, that stand of trees drops resin-rich twigs, that ridge is too damp to be worth the effort. Fuel hunting becomes one of the rhythms of the day, like water collection or foraging for food. It pulls people outward from camp, then back inward to the circle around the fire, hands full of the next few hours of warmth. Managing the fire itself becomes a skill set, almost an art. Someone in the group learns how to bank coals so they'll still be warm at dawn. Another becomes adept at reading smoke and wind, stacking fuel so that sparks blow away from sleeping spots or stored materials. People experiment with mixing fuel types, a base of slow-burning logs, topped with smaller sticks for quick heat when needed. Over time, you get rules of thumb, half-spoken protocols. Don't waste the good dense wood in the middle of the day when a smaller flame will do. Save certain branches for roasting meat. Use smoky fuel to drive off insects or mask the smell of a kill. Keep a separate little fire for delicate tasks, away from the main bonfire. None of this appears in the fossil record directly. What we see instead are repeated ash lenses in the same spots, layers of fine burned material stacked like a slow-motion time-lapse. We infer the daily choreography from those accumulations. Behind each layer, though, is something uniquely human, teaching. Fire is too important to leave to trial and error. A child who experiments alone with open flames may not live long enough to pass on their discoveries. So knowledge has to flow socially. Older individuals show younger ones how to feed a weak ember with breath instead of smothering it, how to build a little teepee of twigs to let air flow, where to place a flat stone to serve as a safe cooking surface, when to step back because the wind is about to shift and blow sparks your way. At first, this teaching might be mostly demonstration and imitation. A toddler watches someone carefully lift hot stones from the edge of a hearth with a forked stick and learns simply that this is a thing people do. Over time, gestures become routines, routines become traditions, and traditions become rules. Who is allowed to tend the fire? Who decides when to let it burn down and when to keep it roaring? Is there always someone on ember duty when the camp moves carrying a smouldering brand to the next site? We don't know the details, but something like this must have existed. The continuity of fire requires the continuity of knowledge. By the time true, well-defined hearths appear in the archaeological record, compact, repeatedly used fire spots in caves like Wonderwork in South Africa, or later at sites occupied by Neanderthals and early Homo sapiens, we're probably looking at communities where fire is no longer a rare visitor. It's a daily presence that everyone knows how to live with. And when fire is that reliable, something subtle but powerful becomes possible. You can plan meals around heat that you expect to have tomorrow, and the next day, and the next. You can choose foods that only really make sense if they're roasted, baked, or simmered. Tough roots, fibrous stems, sinewy cuts of meat, all of them begin to move from fall back if we must to staple if we have time and fuel. Cooking stops being an occasional luxury of lucky days when lightning struck nearby and starts to become a routine option. Maybe not for every meal, not in every season, but regular enough that bodies and cultures can begin to adapt around it. That reliability is the bridge to a new kind of question. If our ancestors could now count on heat often enough to deliberately transform their food, what did that heat actually do? How did it change the calories they could extract, the pathogens they faced, the time they spent chewing, the energy available to their brains and bodies? In other words, once the sparks had been tamed into hearths, what did cooking itself begin to do to food and to the humans who ate it? When you put something over a flame, it doesn't just get warm, it changes from the outside. Cooking looks simple. Raw thing, hot thing, wait a bit, eat. But inside the food, the world is being rearranged. Long chains of molecules twist, break, and reform. Barriers that once kept your saliva and stomach acids at arm's length begin to soften and collapse. To see why this mattered, it helps to start with something deceptively plain: starch. Many wild plant foods our ancestors relied on, roots, tubers, seeds, are loaded with starch granules. These are tiny, tightly packed energy vaults, built by plants to store sugars for themselves, not to make life easy for hungry primates. Raw, those starch granules are semi-crystalline. Water has a hard time getting in. Digestive enzymes even harder. You can chew and chew on a raw tuber and still swallow a lot of calories that pass right through you. Add heat and water, though, and something dramatic happens. At a certain temperature, those starch crystals start to swell. The granules take up water, lose their ordered structure, and burst. This is gelatinization. The starch goes from rigid and glassy to soft and gel-like. For your digestive system, that gel is a gift. Enzymes like amylase can now slip in and rapidly chop long starch chains into shorter sugars. Studies on modern foods show that cooked, gelatinized starch often yields more usable calories than the same food eaten raw. The exact numbers vary by plant and cooking method, but the direction is clear. Heat makes many starches more accessible. This doesn't mean every ancient meal was a bowl of mashed carbohydrates, but for any group that began routinely roasting roots in ashes or simmering them in hot pits, the energy landscape quietly shifted. Plants that had once been backup food in bad times could become reliable staples. Proteins undergo their own transformations. In meat, eggs, and some plant tissues, proteins are folded up like intricate origami. These shapes are stabilized by delicate bonds and interactions. Heat jostles those bonds, breaks them, and lets the protein chains unwind. This is denaturation to you and me. Denaturation looks like a runny egg turning firm, or a translucent strip of flesh turning opaque. To your enzymes, it means fewer hidden corners. Unfolded proteins are easier to grip and break apart into amino acids. In meat, there's another key structure: collagen. It's the tough, rope-like protein in tendons, ligaments, and connective tissue. Raw collagen makes meat chewy, sometimes almost impossible to tear apart with human teeth. But given enough time and heat, especially in the presence of moisture, collagen slowly breaks down into gelatin. That process transforms stringy, resistant tissue into something soft and slippery. A shank that would have taken hours to gnaw and still left your jaw aching can. After long roasting or stewing, fall apart with a gentle pull. The calories and nutrients are the same on paper, but in practice they are much cheaper to extract. Less chewing, less gut work, more net energy for everything else your body needs to do. Heat also tampers with plant defenses. Many wild plants don't really want to be eaten. They pack their seeds and leaves with bitter compounds, enzyme inhibitors, and mild toxins. These anti-nutrients can block the absorption of minerals, interfere with digestion, or make you feel nauseous if you overindulge. Cooking can blunt some of those chemical spikes. Boiling certain beans and seeds reduces lectins and other problematic molecules. Roasting or leaching tubers helps remove cyanogenic compounds and harsh tannins. Not all toxins vanish with heat, and some plants remain dangerous regardless, but fire creates a new relationship with many borderline foods. From avoid unless desperate to safe if prepared correctly, alongside toxins are smaller passengers, microbes and parasites. Raw meat, untreated water, unwashed roots all can host bacteria, worms and protozoa that see your intestines as prime real estate. Heating food to sufficient temperatures kills many of these hitchhikers, or at least reduces their numbers. From the perspective of evolutionary history, this is probably one of the bigger payoffs of cooking, but the evidence is nuanced. We can't sample the gut contents of early Homo on a large scale. What we do see today is that cooking, pasteurization, and boiling water dramatically lower rates of certain infections in modern populations. It's reasonable to suspect that even partial, inconsistent cooking in the past chipped away at disease burdens, especially in environments where carcasses sat warm for hours or were shared between many mouths. So heat helps unlock starch, soften protein, disarm some toxins and cull pathogens. But it also changes something less tangible: desire. When sugars and proteins are heated together on the surface of food, they engage in a set of reactions known collectively as the Maillard reaction. This is the chemistry of browning: the dark crust on roasted meat, the toasty edge of bread, the golden skin of a baked tuber. Maillard products are complex. They produce hundreds of new flavour molecules and aromas: nutty, savoury, caramel-like, roasted. Smoke adds its own compounds, drifting into fat and skin, and turning simple fare into something that smells powerful from a distance. For an early human returning to camp, following that scent plume back to the hearth, cooked food wouldn't just be easier to chew. It would be more tempting. The smell of browning and smoke could guide you to calories the way the smell of ripe fruit guides primates in a forest. Taste shifts too. Bitterness can mellow. Sweetness can intensify as starches partly break down. Fats can render and coat the tongue, carrying flavours more effectively. Over time, preferences can tilt. What once was neutral or even unappealing in its raw state may become highly desirable once roasted or smoked. Of course, there are trade-offs. Heat doesn't only break down plant toxins and bacterial membranes. It can damage vitamins, water-soluble nutrients like vitamin C, and some B vitamins can leach into cooking water or degrade with prolonged high temperatures. Delicate phytochemicals can be lost or transformed. Overcooking or charring foods creates its own set of problematic compounds. Modern toxicology has identified several chemical families formed in burned or heavily smoked food that, in high doses, increase cancer risk in lab animals. Our ancestors were not reading public health advisories, but their bodies still had to cope with whatever long-term effects regular exposure might have had. Then there's the air itself. Sitting around a wood fire means breathing in smoke, a mixture of fine particles and reactive gases. Today, indoor air pollution from cooking fires remains a serious issue in many parts of the world. Eyes water, lungs irritate, long-term respiratory problems accumulate. Ancient hearths tucked into caves or shelters would have posed similar challenges unless cleverly ventilated. So cooking isn't a free upgrade. It's a bundle of advantages wrapped around new risks and costs. Time spent gathering fuel, hours tending coals, smoke in the lungs, some nutrients lost, even as others become easier to access. But taken together, the balance seems to lean in a particular direction. a group that can routinely turn tough roots and sinewy meat into soft, energy-dense meals, while cutting down on at least some toxins and pathogens, probably gains more than it loses. And if that's true, if fire and food together squeezed extra calories and saved extra effort, then the next question almost asks itself. Given many generations of bodies living with cooked diets, what would start to change? Teeth and jaws designed for grinding raw plants, guts built for slow fermentation, daily schedules dominated by chewing and digesting, would those still be optimal in a world where the hearth waits every evening? To explore that, we have to move from chemistry and safety into anatomy and evolution, and ask whether cooking could help reshape the human body itself. This is where the cooking hypothesis enters the story. It starts from a simple observation about bodies and energy. Every organism runs on a budget. Calories come in, are converted, spent, and sometimes stored. There are no free upgrades. If one part of the body becomes more expensive to run, something else usually has to give. Brains are among the most expensive tissues of all. Pound for pound, nervous tissue burns through far more energy than muscle or bone. Your brain is only about 2% of your body weight, yet in a resting adult it can consume around 20% of the available energy. In a child, the proportion can be even higher. Now compare that with our ancestors. Early hominins had smaller brains, heavier jaws, bigger faces, and longer guts. As the fossil record moves forward, especially over the last 2 million years, we see a broad pattern. Brain volumes increasing, teeth and jaw muscles shrinking, rib cages and pelvis shapes hinting at a somewhat shorter, less bulky intestine. This led some researchers to an idea called the expensive tissue hypothesis. It goes like this: certain organs are metabolically costly: brain, gut, liver, heart, kidneys. If you evolve a larger brain, you can't just magically mint extra calories out of nowhere. One way to afford it is to dial back on another expensive system. For primates that shift toward higher quality, easier to digest foods, the gut can be streamlined. Shorter, less voluminous intestines are cheaper to maintain, but only if the diet is energy-dense and relatively easy to process. In that framework, cooking looks like a powerful trick. Heat pre-digests food on the outside. It breaks apart tough plant walls, unravels proteins, softens connective tissue, and reduces some toxins. It cuts chewing time and digestive effort. A cooked diet effectively hands the gut finished or half-finished work. So, in theory, an ape that learns to outsource part of digestion to the fire might be able to shrink its gut and free up energy for a growing brain. This is the core of the cooking hypothesis, that regular, habitual cooking didn't just change what we ate. It changed how much energy we could spare, and that surplus may have helped support the evolution of big, metabolically hungry human brains. Our anatomy today certainly looks different from that of a wild, raw-eating ape. Compared with a chimpanzee or gorilla of similar body weight, humans have smaller teeth, especially the molars and premolars used for grinding, reduced jaw bones and less powerful chewing muscles, flatter faces with shorter snouts and less room for massive muscle attachments, a digestive tract that's relatively short for our size, with a proportionally enlarged small intestine, the site of rapid nutrient absorption, and a reduced large intestine, where slow fermentation of fibrous plant matter happens. These traits are consistent with a diet made up of softer, higher quality foods that are easier to chew and quick to absorb. Cooked roots, roasted meat, pounded and heated seeds all fit that description. But consistency is not the same as proof. Bringing in cooking as the main driver raises several thorny questions. The first is timing. The largest proportional jumps in brain size in our lineage begin well over 1 million years ago. By then, there is evidence of fire use at some sites, but it is patchy, debated, and far from universal. Some archaeologists argue for habitual fire control by around 400,000 years ago or a bit earlier. Others see scattered, intermittent use stretching back further, but not the kind of daily dependence that modern humans have. If regular cooking truly powered big brains, did it begin early enough? Or did early expansions in brain size precede systematic cooking and rely on other dietary shifts? Then there's causality, even if cooking and brain growth overlap in time. That doesn't tell us which way the arrow points. Did fire and soft food enable larger brains by freeing up energy? Or did increasingly clever, social hominins invent and refine cooking because their expanding brains made them better innovators and teachers? The feedback could easily run both ways. Alternative explanations complicate the picture further. Long before anyone was simmering stews, hominins were cracking long bones for marrow and smashing skulls for brains, two extremely rich, soft, fat-heavy foods that require tools more than chewing power. A shift toward more animal fat and meat, even raw but processed with sharp stones, could raise diet quality without involving heat at all. Stone tools also allowed more efficient butchery and plant processing. Scrapers, pounders, and grinders can turn tough tissues into something closer to mash. Some researchers suggest that this kind of mechanical processing, slicing, pounding, mashing, might by itself reduce chewing time and digestive labour enough to favour smaller jaws and guts, with or without fire. Ecology changes too as climates fluctuated. Some lineages moved into open habitats where large herbivores and underground storage organs, bulbs and tubers became increasingly important. Those environments might reward any behaviour that extracts more energy per hour of foraging, whether through cooperative hunting, tool use, or occasional roasting. From this angle, cooking is part of a broader package of strategies that upgrade diet quality: hunting, scavenging, tool processing, marrow extraction, selective foraging. Fire may be a powerful amplifier, but not necessarily the lone cause. The most careful summaries of the evidence tend to land in a middle position. Yes, cooking fits neatly with the expensive tissue idea. Yes, human anatomy and modern experiments on raw versus cooked diets suggest that heat can increase the usable energy from many foods and reduce the cost of chewing and digestion. But no, we cannot point to a single date on a chart and say, here, this is when fire built the human brain. Correlations are strong. Mechanisms are plausible. The details are messy. It is likely that several forces pushed in the same direction: more meat, more fat, more processing by tools, more selective harvesting of calorie-dense plants, and, at some point, regular cooking. Together, over long stretches of time, they created bodies and brains different from those of our ape cousins. To see how those forces show up in the skeleton, how softer, more processed, and eventually cooked foods might literally remodel the face, we need to zoom in on the business end of eating. The teeth, the jaws, and the chewing muscles that once ground through hours of raw foliage every day had to adapt to a new kind of workload. If you feed a machine easier work, the machine can change. Imagine a face built for a lifetime of tearing, crushing, and grinding raw plants and sinewy meat. Thick jawbones, tall faces, broad dental arches, huge chewing muscles anchored to sturdy ridges of bone. This is the classic ape solution to a tough, fibrous diet. You don't outsmart your food, you overpower it. Now imagine, slowly over many generations, that diet begins to shift. More meat stripped with sharp flakes instead of bitten off with the front teeth. Roots cracked, sliced and pounded before they ever reach the mouth. Later, those same foods roasted or baked until they soften, fibers loosening, fats melting, starches swelling and bursting. If each bite is easier to break down, the forces running through the jaws change. Chewing becomes less of a full-body workout. The long daily hours spent mashing raw matter shrink. Mechanical demands on bone and muscle lighten. Bodies grow under pressure. Bone responds to repeated force by thickening. Muscles respond by enlarging. If the pressure eases for long enough in a lineage, both can retreat. Not overnight, not within one lifetime, but step by step across thousands of years. This is one way researchers think about our shrinking faces. Softer, more processed food means lower peak bite forces and fewer massive chewing cycles every day. Reduced workloads make huge jaw muscles less necessary. Without the constant tug of those muscles, the bony scaffolding that supported them can slim down. Brow ridges, cheekbones and jaw angles evolve under new rules. Cooking isn't alone in this. Mechanical processing, cutting, scraping, pounding already moves part of the job outside the mouth. Stone tools take the brunt of work that used to be done by enamel and muscle. Fire just takes it further, finishing the breakdown chemically and structurally. Dental evidence gives us a partial window into this transition. When archaeologists examine fossil teeth, they look at several clues: the size and shape of the crowns, the thickness of enamel, the microscopic scratches and pits on the chewing surfaces, the overall pattern of wear from the sharp, unworn edges of youth to the flattened, polished plates of old age. A diet of hard, brittle foods, nuts, seeds, grit from dusty environments tends to leave different microscopic traces than a diet dominated by tough leaves or raw meat. Heavy abrasion can sand teeth down quickly. Sticky, fibrous foods can produce distinctive scratch patterns. Over time, you can sometimes see a shift from heavily worn, heavily chipped teeth towards somewhat more moderate wear. But this evidence has limits. Teeth wear for many reasons. Diet, yes, but also the grit blown in by the wind, sand stuck to roots, even the use of teeth as tools. Two populations eating similar foods may show different wear, simply because one lived in dustier conditions. And cooking leaves no direct mark on enamel. Its effects are indirect, operating through softer textures and reduced grit in prepared food. So, when we see changes in dental wear over the last 1,000,000 or 2,000,000 years, we can say that chewing lives were changing. We can say that some hominins seem to have shifted toward diets that were, on average, less punishing on the teeth. We cannot look at a pattern of scratches under a microscope and declare, this is the fingerprint of stew. The broader context helps. Tool use and cooking are both forms of what some anthropologists call external digestion. Instead of relying solely on enzymes and gut bacteria inside the body, you start the breakdown process outside, with sharp edges and heat. A sharp flake can turn a raw root into thin slices. A hammerstone can pound seeds into meal. A fire can gelatinize starch, denature proteins, and soften collagen. Each step moves chemical energy a little closer to being absorbable. From the gut's perspective, this is a quiet revolution. Guts are not all the same. Some animals invest heavily in long fermentation-heavy large intestines, where bacteria slowly break down fiber and produce extra calories in the form of fatty acids. Others favor a shorter tract with a proportionally large small intestine, emphasizing rapid absorption of sugars, fats, and proteins from already processed high-quality food. Humans lean toward the second pattern compared with other primates our size. We appear to have a relatively enlarged small intestine and a reduced colon that fits a diet rich in energy-dense items, meat, fat, cooked starches, and relatively poorer in coarse, fermentable fiber. If cooking and tool processing raised the average quality of food, natural selection could favor shorter transit times and smaller fermentation chambers without sacrificing energy yield. A smaller gut is cheaper to build and maintain. Its tissues require blood, oxygen, and constant renewal. Trim that system down, and you potentially free up resources for other expensive organs like the brain. At the same time, a more efficient digestive tract can change the rhythm of life. Consider infancy and childhood. Milk is already an easy, energy-rich food, but in a species that increasingly relies on cooked gruels, mashed tubers, and softened meat. There's another option: earlier weaning. If adults can reliably produce soft, nutrient-dense foods that babies can handle without full sets of teeth, mothers can, in principle, stop breastfeeding sooner. That frees them to conceive again, shortening birth intervals. Over many generations, this can raise population growth. It can also shift the balance of risks. Earlier weaning only works if post-weaning foods are both safe and nourishing. Cooking helps on both counts. It can kill many pathogens and parasites, and it can squeeze more usable energy out of scarce roots or lean meat during hard times. In periods of scarcity, a group able to make otherwise inedible or marginal foods more digestible with pounding and roasting may see more children survive the lean seasons. Those survival differences, repeated again and again, are the quiet engine of evolutionary change. But as always, there are costs alongside the benefits. Control of fire means proximity to smoke. In enclosed shelters or caves, repeated exposure to smoke particles can irritate eyes and airways, inflame lungs, and perhaps contribute to chronic respiratory problems. Soft, sticky cooked foods, especially when combined with sugar-rich plants or later agriculture, may alter dental disease patterns. Burns from open flames, hot stones, boiling liquids become part of everyday risk. Some of these drawbacks are immediate. A child who falls into a hearth, an elder whose lungs struggle in smoky air. Others are slow and cumulative, only noticeable when you step back across centuries. Yet, for our ancestors, the trade seemed to be worth it. Enough calories prepared in enough safe ways could outweigh the dangers of smoke and flame. And once fire and food preparation began pulling bodies in a new direction, lighter jaws, different guts, altered growth rhythms, they also started pulling minds and societies in new direction. Because cooking isn't just about what happens inside the mouth or the intestine. It's about what happens when the group must gather reliably at the same place each evening to tend the flames, share the food and protect the embers. When heat and light become nightly obligations, the hearth stops being a tool and starts becoming a meeting place. That is where the story of our social world really accelerates. A fire that must be tended is a kind of clock. When you rely on embers to carry flame from day to day, you can't wander off whenever you like. Someone has to stay nearby. Someone has to feed in a stick now and then, rake the coals, make sure the wind doesn't scatter everything into darkness. Over time, that obligation starts to set a rhythm. You can imagine it building gradually. At first, fire is something your ancestors might borrow from a lightning strike or a brush fire, using it until it dies and then waiting for the next chance. But as control improves, as they learn to keep embers alive and coax them back into flame, the group's movements begin to orbit around those coals. Certain spots are better for fire than others, sheltered from the wind, close enough to water and fuel, dry enough that the ground doesn't smoulder into hidden roots. Those spots get reused. The blackened circle on the cave floor, the cleared patch among the rocks, the ring of heat-cracked stones by a riverbank. Again and again people return to the same places at the same times of day. This predictability matters. A central hearth becomes a meeting point that everyone can count on. During the day, individuals and small parties may scatter to forage, to hunt, to gather wood. But as the light drops and the air cools, there is a gravitational pull back to the fire. You don't need language to feel this. Other animals have sleeping sites and communal roosts. But once you add heat and cooked food to the equation, the evening gathering becomes more than just a pile of bodies for warmth. It becomes the centre of a daily ritual, Cooking encourages this in a very concrete way. Raw food foragers can, in principle, eat whenever they find something. A fruit here, some leaves there, a scrap of meat torn from a carcass. Meals can be scattered through the day. Cooking concentrates eating. If you have to bring raw ingredients back to a place where fire and tools are, the group's calories begin to funnel toward that point. A root dug in the afternoon isn't eaten on the spot. It's carried home, scraped, sliced, and set near the coals. A hunk of meat isn't gnawed in the field. It's shared, divided, and roasted. That means people show up not just to sleep, but to eat at predictable times. Morning perhaps, and especially evening. Once multiple individuals are tied to the same kitchen, so to speak, new questions arise. Who brings what? Who gets how much? Who waits? And who gets first bite? Food sharing already existed long before hearths. Many primates share meat occasionally. Mothers share with infants. Allies share after a cooperative hunt. But fire and cooking give sharing a new infrastructure. If the most efficient way to use meat and tubers is to pool and cook them together, the daily payoff depends on everyone contributing and everyone accepting a share. That can smooth out bad luck. The hunter who came back empty-handed still eats from the pot. The forager who found nothing one day can rely on yesterday's surplus. Anthropologists studying modern hunter-gatherers see this kind of pooling everywhere. For many groups, the meat from a big animal is not owned by the individual who killed it, but by the camp as a whole. Portions are distributed according to custom. People build reputations as generous sharers or stingy hoarders. It's easy to imagine that once regular cooking became common in the deep past, similar logic started to take shape. Over time, this could turn into a quiet, powerful system of reciprocity. You bring food today, someone else brings food tomorrow. You don't keep score in a strict accounting sense, but people remember patterns. Chronic freeloaders might find themselves subtly pushed to the margins. Consistent providers might gain status, allies, and better mating opportunities. But cooking also creates new temptations. Raw food is often consumed immediately, close to where it's found. There's not much time to steal it. A pot simmering by the fire is different. Food is visible. You can smell the fat, hear the crackle. It sits there, accumulating value, vulnerable to anyone who reaches out a hand. That vulnerability invites rules. Who is allowed to take from the pot? Do you have to ask, does the cook control the ladle? If someone tries to hoard or to sneak extra portions, what happens? The archaeological record can't give us direct footage of these negotiations, but we can see hints of increasing structure, repeated hearths, evidence of designated activity zones around fires, standardized tools for cutting, stirring, roasting. Ethnographic parallels suggest that as resources become more central and more easily monopolized, groups often respond with explicit norms to prevent chaos. Taboos about eating before elders, customs about sharing with in-laws, expectations that children will be fed before adults. Fire needs guarding, cooked food needs guarding, and guarding in turn demands trust. It's easier to leave your pot unattended for a moment if you believe your neighbours won't rob you blind. That belief doesn't spring from nowhere. It comes from long histories of enforcement, gossip, and shared expectation. We don't do that here. Over many generations, such expectations become part of the invisible architecture of society. Some researchers even argue that the demands of cooking and food sharing played a role in shaping human pair bonding and parenting patterns. The idea in one version goes like this. As infants were weaned earlier onto soft-cooked foods, the job of provisioning children became more complicated. Mothers juggling frequent births might struggle to supply everything alone. A reliable partner invested in both the mother and the offspring could provide meat and protect resources at the hearth. Cooperative parenting, with fathers, grandparents, and other relatives contributing, would further spread the load. In this view, the hearth is not just where food is prepared, it is where family structures crystallize. Pair bonds could be reinforced during shared evening meals, alliances between kin groups renewed as they eat from the same fire. Not everyone agrees on the details. Human mating and parenting systems are messy, flexible, and shaped by many forces: ecology, predation, social competition, disease. But it's hard to ignore how often, in later societies, core relationships are anchored by shared meals and a shared fire. There may be deep roots to that pattern. Then there is the simple, underrated fact of waiting. Cooking takes time. Meat has to roast through. Tubers need to soften. Grains must be pounded, soaked, heated. You can't speed physics much with bare hands and stone tools. So people wait. They sit near the flames, watching, turning, tending. They have minutes or hours that are not fully occupied by foraging, walking, or intense labour. That slack time is fertile ground for social interaction. Conversation, if language is advanced enough, can bloom here. So can quieter forms of communication: grooming, gestures, shared glances, teaching by demonstration. A child might watch a grandparent shape a tool or tell, in halting phrases, how to avoid a dangerous ravine. Adults might quietly negotiate future plans. Who hunts where tomorrow? Who travels with whom? Which strangers can be trusted? This waiting together is a different kind of social glue than frantic daytime cooperation. It's low pressure, repetitive, nightly. Over countless evenings, it can deepen bonds in ways that sporadic, high-stress hunts do not. And with repetition, patterns harden into custom. Someone takes responsibility for keeping the fire alive through the night, perhaps rotating among households or assigned to particular individuals. Someone is known as the best firemaker or cook. Certain people might always sit closest to the warmth. Elders, respected hunters, nursing mothers, while others hover on the perimeter. These patterns teach everyone, especially children, where they fit in the social order. From here, it's a short step to more elaborate norms. Maybe some foods are reserved for specific ages or statuses. Maybe there are quiet rituals before the first bite. Maybe you don't speak of certain topics while the pot is boiling. These conventions are small on their own, but together they create a shared sense of how we do things, centered on the hearth. As evening deepens, another dimension of fire comes to the foreground. Light. A controlled flame pushes back the darkness beyond what a bare eye could manage. It carves out a circle of visibility in a world still inhabited by predators, sudden noises, and unseen dangers. Staying inside that circle affects when and how people sleep. It allows some to remain active a bit longer, to prepare tomorrow's tools, to repair clothing, to tell children one more story before they drift off. In the glow of that light, with bellies warmed by cooked food and the day's work mostly done, another transformation begins. The hearth stops being only a place of calories and coordination and becomes the stage for something else entirely: shared imagination. To follow that trail, we have to step fully into the night, when most of the world is asleep, and see what humans do when darkness no longer means immediate silence. Owning the night starts with something very simple. You don't have to go to sleep when the sun disappears. For millions of years before controlled fire, darkness was a hard boundary. Most primates wind down with the light. Vision is their main defense, and without it, moving around becomes dangerous. You find a safe perch, huddle close, and wait for dawn. Fire softens that boundary. A camp with a hearth can stretch the waking day. Not indefinitely, ancient humans weren't pulling all-nighters with espresso and lanterns, but by an hour here, 2 hours there. enough time to do things that weren't possible before. Tools can be finished after sunset. Hides can be scraped, sinew twisted into cord, spear points retouched, baskets mended. A mother can soothe a restless child while still seeing the ground. An elder with stiff joints can sit and work in warmth instead of fumbling in the cold. This doesn't just add tasks, it reshapes the whole daily rhythm. If evenings are reliably lit and warm, some work naturally drifts into that slot. Daylight hours become more focused on ranging outward, tracking, gathering, hauling fuel. Night concentrates inward, maintenance, conversation, planning. Sleep might slide later, perhaps in exchange for longer rest in the cool morning. Over many generations, groups that used these extended hours efficiently could squeeze more learning, more cooperation, more subtle coordination into each 24-hour cycle. Owning the night also has a psychological dimension, the feeling of being safe in a dangerous world. Predators see differently than we do. Big cats, hyenas, canids, many of them hunt by smell and sound as much as by sight. A fire is no magical force field. Fossil bite marks, rare but real, on hominin bones, remind us that early humans were sometimes still prey. Yet fire changes the equation. Many animals do seem wary of open flame, especially at close range. The heat, the flickering light, the sharp crackle are foreign to them. Experiments with modern wildlife show mixed results. Some predators keep their distance, others become curious or even attracted, especially if cooking smells are strong, but the general pattern suggests a ring of hesitation. Inside that uncertain ring, humans could feel, and often be, somewhat safer. The important part may be less the strict physical protection, and more the predictable, shared sense of refuge. Knowing that your group will regroup around a lit hearth each night creates a mental anchor. Children learn that the glowing circle is where adults are alert, where weapons are near at hand, where extra eyes and ears are watching the dark. Even if the real risk reduction is modest, the perceived reduction matters. It lowers constant vigilance just enough to allow other things to happen. Once people are no longer braced in silent fear every night, attention can move from what is out there to what is in here. In that shift, the birthplace of stories becomes possible. Imagine a long day's labour ending, bellies warm with roasted meat or softened tubers. The fiercest hunger dulled, hands occupied only lightly, turning a spit, nudging a coal, rubbing smoke from stinging eyes. There is finally spare mental bandwidth. In these moments, language, if it existed in even a simple form, finds room to stretch. Someone can recount the day's hunt in more detail than pure necessity demands, where the herd turned, where the ground gave way, where a cliff almost claimed a brother. Another person can respond not with immediate action, but with commentary, humour, embellishment. A child can ask why, and not be shushed because everyone is rushing to the next urgent task. Even in groups with minimal spoken language, gesture and expression can build proto-stories. A sequence of mimed actions, a repeated sound for a specific animal, a shared laugh at the same moment each retelling. Night after night, those patterns become narratives. Storytelling, in this sense, is not entertainment tacked on at the end of a productive day. It becomes a tool for memory. Firelit evenings are a perfect environment for consolidating information. The same people sit in roughly the same places, at roughly the same time, facing the same focal point. Shared light pulls their gaze in one direction. Shared warmth regulates their bodies. Shared food has already synchronized their internal clocks. This is an ideal setup for what psychologists call joint attention, many minds focusing together on the same thing. Under these conditions, teaching and remembering become easier. A hunter can describe where dangerous animals den, tracing shapes in the dirt by the glow. A gatherer can list which plants are safe only in the wet season, which roots must be leached before roasting. Elders can retell origin myths, migration paths, genealogies, whether in full language or in more fragmentary proto-speech, embedding practical instructions inside memorable plots. Children don't just learn facts, they learn them wrapped in emotion. Fear during the tale of the child who ignored a warning. Relief when the hero listens and survives, or when an ancestor outwits a predator. Emotionally charged memories stick. Firelight, by clustering bodies and synchronizing moods, amplifies that process. Around the hearth, social cohesion thickens. Sharing a fire means sharing attention, sharing emotional rhythms, even sharing silence. You watch the same sparks. You flinch at the same distant call. You laugh at the same clumsy stumble. Over time, these synchronized experiences knit people together in ways that are hard to see but easy to feel. The simple routines of fire tending play a role too. Feeding embers, rearranging logs, blowing gently on a fading coal, turning food so it doesn't burn on one side. These are repetitive, almost meditative actions. For the person doing them, they can induce a kind of calm focus. For the rest of the group, they provide a soothing background, the steady scrape of wood, the occasional crack, the predictable movements of a familiar hand. Modern studies of repetitive manual work, knitting, whittling, sweeping show that these actions can reduce anxiety and help people process thoughts. It's not hard to imagine a similar effect in deep time. As hands keep the flame alive, minds wander through the day's events, through remembered advice, through imagined futures. Planning in this quiet way becomes habitual, and fire encourages a more concrete kind of planning too. Cooking rewards foresight. You can't eat what you didn't save. If you want something warm at dusk, you must think about it earlier, set aside fuel, carry back the right roots, resist the urge to devour all the meat raw on the spot. You must also think about tomorrow's fire, whether enough embers will survive the night, whether someone is assigned to guard them, whether today's surplus should be dried or smoked. These may seem like small decisions, but they push the mind toward the future. Individuals who can hold in their heads a sequence of steps, gather now, store here, cook then, share later, are better positioned to benefit from the hearth. Groups that organize themselves around such anticipatory skills can buffer lean times more effectively. Over long spans of evolutionary time, selection may have favored brains that were better at this slow, deliberate kind of thinking. Less impulse, more patience, less immediate gratification, more expectation. So, by the time the fire has burned low and most of the camp has curled into sleep, something new has entered the world. Nights filled not only with fear and fatigue, but with learning, with memory, with shared imagination and quiet planning. Once you can control heat well enough to own those hours, another question naturally arises. If this same invisible force can soften roots, harden points, and bend the rhythm of the day itself, what else could it change? If you can shape food with fire, can you also shape stone, bone, clay? Can heat become not just a way to survive the night, but a tool to transform the very materials of your world? To answer that, we have to look more closely at fire, not just as a hearth, but as a workshop. If you sit long enough beside a working fire, patterns start to emerge. You notice that a green stick, fresh from a living tree, smoulders and smokes. A dead, dry branch catches more eagerly and burns hotter. A half-burned log glows red at the core and black on the outside. Poke it, and bright embers flare where the air can reach. Bones crack and sometimes explode. Fat drips, flares and vanishes. Wet things hiss, dry things blacken. Some stones split with a sharp report. Others just redden quietly and cool again, never quite the same shape as before. Cooking belongs to this larger web of observations. It is one special case in a broader experiment. What happens when you apply controlled heat to the solid things around you? Once early humans had even rough control over hearths, keeping coals alive, feeding fuel steadily. They were already accidentally running experiments in material science. A spear propped too close to the fire stiffens, the tip darkening and hardening. A digging stick, once scorched, scrapes packed earth more sharply. A bundle of plant fibres, dried by a smoky edge of the flames, resists rot better than a green cord left out in the rain. Hardening wood with fire seems to have been one of the earliest deliberate uses of heat beyond cooking. You don't need complex theory to stumble on it. Try to dry a stick quickly. Notice that it becomes rigid and slightly charred, and then feel that it bites deeper into the ground or into an animal's hide. Experimental archaeologists today can reproduce the effect with simple hearths, and some of the oldest wooden spears found in Europe show surface changes consistent with light charring. The dates are debated, the interpretations cautious, but the principle is clear: fire can sharpen, not just soften. The same is true of drying more generally. Once people were regularly roasting meat and roots, they would have seen how food near the edge of the heat dried instead of fully cooking, turning tough but long-lasting. Hang thin strips of meat where the smoke curls away, and you get something closer to jerky than to a fresh roast. Lay seeds or sliced tubers near warm stones, and they store a little longer before mould claims them. This is food technology, but it also opens the door to other drying projects. If you can dry food, you can dry fuel for tomorrow. You can dry cordage so it doesn't rot as fast. You can dry hides before you scrape them, noticing that warmth and low steady heat make the work easier. You might even experiment with smoking insect-repelling plants over sleeping areas or gear, discovering by trial that some smokes preserve while others ruin. Step by step, cooking, drying and hardening feed into a shared skill, managing heat gradients. Too close and things burn, too far and nothing changes. Just right, and materials transform in useful ways. From here, adhesives and composite tools become thinkable. Many plants exude resins and gums. Tree sap that oozes near a fire will bubble, thicken, and set harder as it cools. Lumps of pitch might drop onto hot stones, melt, and then re-harden in a new, more brittle form. If you have ever had sticky sap on your hands and watched it change by the fire, the idea that someone could eventually press that softened resin between a stone point and a wooden shaft is not far-fetched. In later Neanderthal and early Homo sapiens sites, there is direct evidence of this kind of adhesive technology. Birch bark tar, carefully produced by heating bark in low oxygen conditions, then used to haft stone tools onto handles. That level of control, excluding air, maintaining a steady temperature, almost certainly came long after simple cooking fires. But the path toward it likely wound through countless small experiments at the hearth's edge: pitch on fingers, resin dripped on coals, sticky lumps smeared on tool fractures to see what happens, composite tools, stone plus wood plus fibre plus glue, are a mental leap as much as a technical one. You have to imagine that a spear is not just one thing, but a system of parts, each with different properties that heat can modify. Fire becomes a partner in design. Once fire is seen this way, the hearth itself starts to change shape. Early fires may have been little more than open patches of burning fuel on the ground. Over time, people begin to notice that wind disrupts flames, that embers last longer under ash, that certain arrangements of stones reflect or concentrate heat. Someone piles a ring of rocks to keep the coals in place. Someone else digs a shallow depression to shelter a smouldering bed from the breeze. These are small steps towards something new, managed heat spaces. From here, the leap to pits and ovens is less dramatic than it sounds. In many later hunter-gatherer and early farming societies, earth ovens appear, holes lined with heated stones, filled with food, then sealed with soil or vegetation to trap heat. Archaeological traces of such structures go back tens of thousands of years in some regions, though the exact dates and independent inventions are still argued. The logic, however, is simple enough that it could have been discovered many times. Heated stones continue to radiate warmth long after the visible flames die. Bury food with them and you can cook slowly, evenly, with far less fuel and attention. Stone boiling is another variant. In areas where direct flames would burn containers, people heated rocks in the fire, then dropped them into water-filled pits or baskets lined with hide, bark or stomach. The sizzling shock of hot stone in cool liquid is memorable. It turns an ordinary hearth into a variable temperature device. You can control how hot the water gets, how fast, and for how long, just by adding or removing stones. All of this depends on something that cooking itself encourages: the habit of using containers. Even before ceramics, people had ways to hold water and food. Folded leaves, hollowed gourds, sewn skin bags, woven baskets made watertight with pitch or clay. Repeated cooking pushes these technologies forward. If you often need to soak bitter roots before roasting, or mash cooked seeds into pastes, or carry broth from one camp to another, better containers are worth the effort. Baskets that can resist a little heat allow hot stones to be dropped in. Clay daubed on woven walls to protect them from charring accidentally suggests that clay itself can be shaped and hardened. In some parts of the world, fragments of fired clay with impressions of basket weaving appear before full pottery vessels. It is possible, though not certain, that experiments at the edge of the hearth gradually nudged people toward the idea that clay, plus controlled heat, could stand alone as a container. Regional variation threads through all of this. In heavily forested areas, with abundant wood and bark, people might emphasize resin adhesives, smoke curing, and bark containers. On open grasslands with scarce large trees but plentiful stone, the focus could fall more on heated rocks, earth ovens and bone or horn components in tools. In cold, treeless environments, where fuel is precious, innovation might center on insulated pits, careful ember conservation, and maximizing the value of every scrap of fat and bone that touches the flame. Different fuels also invite different inventions. Softwood burns fast and hot, hardwood gives long-lasting coals, dried dung smoulders and smokes. Charcoal, whether used knowingly or simply encountered as yesterday's burned wood, burns cleaner and hotter than raw logs, making some higher temperature experiments possible, subtle heat treatment of stone, or more reliable tar production. The archaeological record for specific procedures is patchy, and archaeologists often debate whether a given burnt patch is an accident, a cooking spot, a kiln, or a ritual feature. But taken together, the evidence suggests a slow widening of what fire could mean. Cooking remains at the center of this widening circle. Meals provide the daily reason to light and tend a flame. But around that necessity, a halo of other heat tasks grows: drying, hardening, gluing, boiling, baking. Over generations, those skills become part of a group's identity, tuned to local landscapes and materials. So as human bands moved into new territories, new climates, new stones, new plants, they didn't just carry recipes. They carried a way of thinking about heat itself as something that could be directed, stored, trapped, intensified, or softened. In each new place, that mindset met new possibilities. In the next phase of the story, we'll watch what happens when this portable fire culture spreads across the planet, and cooking begins to diverge into many different traditions, each shaped by its own ecology, its own fuels, and its own imagination. When small bands began to leave their familiar homelands, they weren't just walking bodies through new landscapes. They were carrying a portable theory of heat, but that theory had to negotiate with reality everywhere it went. Imagine a group stepping out of a wooded river valley into open grassland. At first glance, there is space, game, and light. But there is also a problem. Fewer big trees. Wood, the default fuel, becomes sparse. Fires must shrink. People learn to prize slow, coal-rich burns, to use brush, twigs, roots, and whatever else will catch. On treeless steppes and high plateaus, the lesson is even harsher. Wind strips heat away, flames gutter. Here the hearth moves downward. Pits are dug deeper, lined with stone, sheltered from the constant tug of the air. Dried dung from grazing herds, shrubs, and twisted roots become fuel. Fire is no longer something you build high and bright. It is something you protect, bank, and hide from the sky. In damp forests, the challenge flips. There are trees everywhere, and yet everything is wet. Green wood smokes and sputters. To cook at all, people learn to seek deadfall under overhangs, to strip bark that traps drier layers beneath, to stack and season fuel days or weeks ahead. Cooking becomes a dance with humidity, keeping enough heat to penetrate soaked fibres without drowning the hearth in steam. Altitude adds another constraint. As humans climbed into highlands, water boiled at lower temperatures. Stews simmered but never quite reached the fierce, rolling boil a lowland cook might expect. Tough meat stayed tough. Roots refused to soften on schedule. The answer in many places leaned back on techniques that did not rely on the boiling point of water alone. Pit ovens with stored stone heat, long slow roasting, or combining moist and dry heat in clever ways. Across all these environments, certain methods appear again and again, like rhymes in a long song. Roasting is the simplest, food exposed directly to radiant heat, on sticks, on flat stones, or tucked near embers. It asks little more than a flame and patience. From coastal shallows to mountain valleys, roasting likely remained the first-line technique, quick, visible, easy to adjust. Pit cooking is slower and more elaborate. It works especially well where fuel is precious or winds are fierce. Heat is stored in buried stones, in insulating earth, in layers of vegetation. Once sealed, a pit oven can cook without constant attention, turning tough, fibrous roots or sinewy meat into something yielding and sweet. In many regions, versions of this method appear deep in the archaeological record, perhaps invented and reinvented countless times. Steaming emerges wherever people combine enclosed spaces with moisture. In some places that means wrapping food in leaves and nestling it in embers, in others, covering pits with wet vegetation. Steaming does something subtle but important. It softens without charring. Delicate fish, leafy greens, and small shellfish benefit from this gentler heat, becoming edible without losing as much mass to scorching. Smoking bridges cooking and preservation. It is especially valuable near coasts, lakes and rivers, where fish runs or shellfish beds produce sudden surpluses. A single lucky day on a salmon river or tidal flat can overwhelm immediate appetites. Smoke curing offers a way to stretch that luck into leaner times. Hung above a low, steady fire, food absorbs compounds that slow rot and repel insects. In cold or windy regions, where open drying is risky, smoke becomes a kind of invisible armour around the meal. Stone boiling appears wherever containers meet fuel constraints. You heat rocks in the fire, then move the heat into water-filled pits, baskets or skins. This method is especially gentle on fragile containers and kind to scarce fuel, because the fire can burn hot and brief while the stones continue to give up their warmth. Grains, small seeds and mixed stews all become possible with this trick, allowing more varied diets in places where direct flames would be too harsh. Underlying these techniques is a simple fact. Different staple foods ask for different strategies. In root-rich regions where tubers and underground storage organs dominate, people lean heavily on long, slow, moist heat. Many wild tubers are full of toxins or stubborn starches. Only careful roasting, steaming or earth oven baking makes them safe and digestible. In such landscapes, knowing exactly how long to bake a specific root and in which kind of pit can be the line between nourishment and poisoning. Where grains and small seeds become important, the focus shifts toward drying, parching and boiling. Seeds must be loosened from husks, kept from sprouting, then softened again for eating. Light roasting makes grinding easier. Boiling turns hard kernels into porridges or pastes. Over time, the rhythm of soak, grind, heat and stir becomes as ingrained in daily life as tending the fire itself. In game-rich areas, cooking strategies emphasize handling meat and fat. Quick roasting delivers immediate calories, but smoking and drying protect surplus. Bone marrow, sinew and organ meats all demand their own techniques to extract maximum value, especially in cold climates where every fraction of fat matters. Fire allows nothing to be wasted for long. On coasts and river margins, fish and shellfish reshape the hearth. Many shellfish are technically edible raw, but cooking opens them more easily, kills parasites, and reveals flavors people quickly learn to crave. Simple roasting on embers, steaming under seaweed, or stone boiling in brine all unfold here, turning tidal pulses into predictable feasts. In all of these settings, fire makes marginal foods reliable. Bitter roots that would be inedible raw become staples once leached and roasted. Hard seeds that would pass straight through the gut become the basis of gruels and breads. Tough cuts of meat, unchewable by a purely raw-eating ape, become soft, shreddable and safe after hours in an earth oven. Even at high altitudes or on sparse steppes. Where options are few, careful management of heat makes the difference between scraping by and building a buffer of preserved food against the next storm. And as people learned to coax value from these difficult foods, they also began to encode their tricks in culture. A method tried one evening becomes a story told the next. Don't dig the pit there, the wind is wrong. Don't eat that root unless the skins have split and the steam smells sweet. Over time, such advice condenses into shared rules, taboos, recipes. Techniques become part of identity. Our people smoke this way. Our people line pits with that plant. Our people never cook fish with this wood. Knowledge travels with marriages, visits and trade. A better way to steam or roast might spread along exchange routes faster than the tools themselves. At the same time, each landscape pushes back, ensuring that no single right way of cooking takes over. What works near a humid delta fails on a dry plateau. What is fuel efficient in a tundra is wasteful in rainforest. This is still long before restaurants or written cookbooks. Deep prehistory remains the domain of small bands, seasonal camps and hearths rebuilt again and again on shifting ground. Yet already heat traditions are diverging, specializing, adapting, rooted in ecology, carried in memory, expressed in daily meals. In the next turn of the story, something profound will happen. Instead of wandering to where food appears, some groups will begin to bring food to themselves. Plants will be sown, animals penned, and fires lit in places meant to last. Cooking, which has followed people across shifting climates, will find new homes in permanent spaces, the first real kitchens of an agricultural world. When people first began to stay put, the change probably felt small. Maybe it started with a patch of wild grain they liked, a stand of nut trees, a stretch of floodplain that always seemed generous after the rains. Instead of just passing through, they came back, cleared a little more, broke the soil with sticks, dropped a few seeds from last season's good harvest. At first, they were still hunters and foragers who happened to garden on the side. But the logic of plants is patient and relentless. Seeds ripen all at once, grains demand threshing, tubers grow in heavy clustered beds. The more you rely on them, the more your calendar bends around their schedule. Cooking follows, in a wandering life. Fire adapts to whatever the land offers that day. Roots here, fish there, a lucky kill once in a while. With farming, the opposite happens. Diet begins to orbit a few starchy staples. Cereals like wheat, barley, millet, rice, pulses like lentils and peas, domesticated tubers, later potatoes, yams, taro. Most of these are terrible foods if you don't cook them. Raw grains are hard, sharp, and full of tightly packed starches the gut struggles to unpack. Many pulses hide bitter compounds and lectins that can make you sick. Some domesticated roots are almost inedible without long, sustained heat. So as fields spread and herds graze nearby, the hearth settles into a new role, not just improving food, but making the main food possible at all. You can feel the shift in daily rhythm. Instead of waiting for a lucky hunt, people wake knowing what breakfast will be, what lunch will be, what tonight's meal will be. Porridges, flatbreads, baked roots, stews thick with grains. The details vary from valley to valley, continent to continent, but the pattern holds. Starch, transformed by heat, moves to the centre of the plate. Once crops become central, storage follows. Harvests come in pulses, sudden overwhelming abundance that has to last through the lean months. Granaries, pits lined with clay, woven baskets sealed with ash or fat. All of these create a new problem and a new opportunity. You now have piles of food that can spoil, mould, or be eaten by pests. But you also have something else. Surplus. More calories than the band needs today. Cooking schedules start to wrap around this surplus. Grain needs drying and parching so it will store. Some of it must be roasted before grinding. Some is boiled into daily porridge. Some is turned into festival foods that take days to prepare. And the hearth itself settles down. Instead of being scraped together anew at every camp, fire is now anchored in installations, stone-lined hearths, clay platforms, semi-permanent ovens. Archaeologists find thick ash lenses, discarded potsherds, fire-reddened earth that mark these as long-used cooking spots. New tools cluster around them. Grinding stones appear, and then multiply. First simple handstones against a larger rock, then carefully shaped querns, mortars and pestles. Hour after hour, people lean their weight into grain, cracking husks and crushing starch. Pottery emerges in many farming societies, transforming how heat can be used. Clay vessels tolerate slow simmering, gentle boiling, and long steeps that would destroy baskets or skins. Ovens from simple clay domes to tandoor-like pits allow bread and flatbreads to puff and blister against hot walls. With these tools, cooking changes shape. It becomes less about the immediate flame and more about managing stored heat. Hot stones that hold warmth, oven walls that radiate slowly, thick pots that keep stews bubbling at the edge of a boil. Social life changes with it. When food is hunted, meals are often episodic. Feast after a big kill, lean days in between. With farming, there is usually something grain in the pot, roots in the pit, even if meat is scarce. Communal meals begin to anchor in predictable times: morning porridge, evening stew, bread from a shared oven. In many early villages, baking and boiling are not just private acts. Shared ovens and large pots suggest coordinated use. Neighbours time their doughs, take turns, argue, gossip. Feasts emerge when harvest is good or when leaders need to display power. Surplus grain can be brewed into alcohol, slaughtered animals can be roasted in quantity, and the scale of cooking becomes a political tool. Who gets invited to eat? Who controls access to stored food? Who manages the hearths that feed many? These questions grow teeth. Inequality creeps in, often wrapped in the gentle routines of food preparation. Some households control bigger granaries or the best land. Some individuals, usually women in many agricultural societies, carry much of the grinding, stirring, baking and cleaning. Others, priests, chiefs, warriors, might eat more meat, finer bread, special festival dishes, their status reflected quietly in what appears in their bowls and how it has been cooked. The kitchen, in this sense, becomes infrastructure, not a private choice about what to eat tonight, but a system of tools, spaces, schedules and social rules that organises daily life. Yet this new stability is not free. As houses cluster and hearths move indoors, smoke accumulates. Lungs, eyes and hearts pay a price for years of breathing particulates in poorly vented rooms. Soot stains ceilings and blackens clay. In skeletons from early farming communities, archaeologists sometimes see signs of chronic respiratory stress, especially in those most tied to the fire. Crowded living brings new pathogens. The same walls that shelter the hearth also trap diseases. Close quarters with domesticated animals introduce fresh parasites and infections. And diet, once broad and varied, often narrows. In many early farming regions, people rely heavily on one or two crops. Millet gruel day after day, wheat bread and lentil stew, rice and little else. Cooking makes these staples digestible and comforting, but it cannot conjure missing nutrients out of nothing. Evidence of anemia, dental defects, and stunted growth appear in some early agricultural skeletons, even as caloric security improves. So the agricultural kitchen is a paradox. It offers reliability and routine, the comfort of a pot that is almost always simmering, the warmth of shared meals, the possibility of planned feasts. But it also locks people into laborious tasks, smoky air, and a diet that can become monotonous. For our story, though, one aspect matters especially: visibility. Fixed hearths, grinding stones worn smooth by generations, ovens rebuilt in the same corner of the same house, pottery sherds with burnt residues clinging inside. These become clear, durable traces. Bones split and scorched next to storage pits, grains puffed and cracked by heat, microscopic starch granules fused on ancient tools all whisper the same thing: here. Cooking was no longer occasional. It was central, systematic, and built into the architecture of life. In the next part, we'll follow those traces more closely. We'll look at how scientists rid burned bones, blackened pots, chemical signatures, and even microscopic soot to reconstruct what people actually did with their fires, and what exactly they were eating when they gathered around those ancient hearths. When archaeologists say, people here were cooking, they're not guessing from a vibe. They're reading traces. The past doesn't come with a menu, but it does leave chemistry, scars and crumbs. Some of the most powerful clues are invisible to the naked eye, the atoms themselves. Every plant and animal on Earth is built from a mix of stable isotopes, slightly different versions of the same element. Carbon, nitrogen, even oxygen. These isotopes behave almost the same in chemistry, but not quite, and tiny differences in how they're taken up and passed along create patterns. Think of it as a faint chemical accent that shifts as you move through the food chain. Plants fix carbon from the air, but different kinds of plants, grasses versus trees, temperate versus tropical, leave slightly different carbon signatures. Herbivores eat those plants and their tissues take on those signatures with a small shift. Carnivores eat the herbivores and shift again. Nitrogen especially tends to step up with each move up the food chain. By drilling a thin slice of tooth enamel or bone from an ancient human or animal, cleaning it and running it through a mass spectrometer, researchers can measure those isotope ratios. The numbers don't tell you roasted antelope with a side of millet, but they can say things like, this person ate a lot of animal protein relative to plants. This group relied heavily on grass-based foods, grains, grazing animals, or both. These individuals grew up near the sea and ate marine foods, while their neighbours didn't. Over time, as more samples accumulate, patterns emerge. Shifts from low to high nitrogen can hint at a growing dependence on meat or fish. Changes in carbon signatures can signal the arrival of new crops, like maize in the Americas or millet in Eurasia. In some late Stone Age and early farming communities, isotope data suggest diets becoming more grain-heavy and less wild diverse, just what you'd expect as fields and cooking pots take over. But isotopes can't tell you exactly what was on the fire, or how it was prepared. For that, we zoom in again, this time to the scale of dust. On the teeth of ancient humans and Neanderthals, and sometimes even earlier hominins, archaeologists find dental calculus. That's the hardened plaque your dentist scrapes off. But fossilized, it's gross, and it's a gold mine. Trapped inside that mineral crust are microfossils, tiny starch grains, fragments of plant tissue called phytoliths, even occasional bits of charred food. Under a microscope, some of these can be matched to plant families, sometimes even specific crops. Wheat starch looks different from barley. Legumes have their own shapes. Roots and tubers leave another kind of trace. Some of these starch granules show signs of having been heated. They swell, crack, gelatinize in characteristic ways. That suggests not only that a plant was eaten, but that it was probably cooked, boiled, roasted, or baked before it ever touched the teeth. Residues cling to tools and pots as well. A stone grinding slab might hold ground in starch from wild grasses or early domesticated cereals. The inside of a pot can preserve thin films of fats and oils, sometimes identifiable as coming from ruminants, pigs, fish, or dairy. Occasionally, layers of visible char at the bottom of a vessel are essentially carbonized stew, a burnt offering to future science. Bones add yet another voice to the chorus. When animals are butchered, stone tools leave telltale marks, fine, V-shaped cuts where muscles were detached from bone, impact scars where long bones were struck to get at the marrow. Under a microscope, cut marks made by sharp edges look very different from gnaw marks left by carnivores. Fire leaves its own signature. Bone that has been lightly roasted turns brownish or black, the collagen inside altered but not destroyed. Bone thrown into a very hot, oxygen-rich fire can turn grey or even chalky white. The collagen burned away and the mineral structure changed. A single burned bone near a hearth might just be trash. But when you find dense clusters of bones with consistent cut marks, repeated patterns of breakage for marrow extraction, and uniform burning that suggests roasting temperatures rather than random scorching, a different picture emerges. You begin to see cooking areas, not just fires where people tossed whatever was left over. Archaeologists pay close attention to context. Bones mixed with ash, hearth, stones, and food processing tools, all in the same layer, argue for meals. Bones burned only at the tips or showing patterns of grease rendering may indicate deliberate culinary techniques rather than accidental charring. Still, there's only so much you can infer from static traces. That's where experimental archaeology comes in. To understand how a particular kind of burning or residue pattern forms, researchers replicate the process. They build hearths like the ones they see in the ground, same kind of stones, same layouts, same wood, if they can get it. They butcher animal carcasses with replica stone tools, cook meat over open flames, in earth ovens, directly on embers. Then they let the whole scene decay, and finally they excavate it as if it were ancient. By comparing the experimental results with real sites, they can say, this pattern of ash and scorched stones looks like repeated low-temperature cooking, not a single catastrophic house fire. Or these cracking patterns on bone match, slow roasting much more than quick disposal in a trash fire. Similar experiments with grinding stones, pottery, and even smoke-blackened ceilings help calibrate our interpretations. How much smoke does it take to leave a certain kind of soot? How many times do you have to use a hearth before its soil turns that distinctive red? All of this, though, unfolds under a cloud of uncertainty. The archaeological record is biased from the start. Soft plant tissues rot quickly, meats and fats vanish unless conditions are perfect. What survives best are the durable things: bone, stone, fired clay, carbonized bits that happen to burn just enough to resist decay. Many sites have been disturbed by later building, erosion, burrowing animals, or human activity. Sampling is never complete. We only excavate parts of most sites, and even there, we only see what our methods allow us to see. Isotope data depend on which individuals were buried and preserved, and they average diets over years, even decades, smoothing out daily variation. Interpretation sits on top of all these filters. Is a charred seed evidence of deliberate parching, or a grain that fell into the fire by accident? Do heat-altered starches on teeth always mean cooking, or can some changes happen in the mouth itself? When isotope values shift, is that because of diet or changes in climate and local ecosystems? No single line of evidence can answer these questions alone. But when isotopes, dental calculus, residues, bones and experiments all point in the same direction, confidence grows. A population whose bones show high reliance on grains, whose tooth calculus is full of heated cereal starch, whose houses contain fixed hearths and ovens with baked-on residues, whose animal bones cluster in patterned roasted heaps, there the case for systematic cooking is strong. When signals conflict, claims weaken, theories get revised, and new questions appear. Working through this slow, layered detective story brings us back to our central mystery. As we trace the rise of cooked grains, roasted meats, boiled stews and baked breads across thousands of years and many continents, we have to ask, was cooking the fire that made us modern, reshaping our bodies, our brains, our societies? Or was it a mirror, reflecting changes already underway in how we lived, cooperated and thought? In the next part, we'll pull the threads together, weighing the evidence you've just seen. We'll sit once more by those ancient hearths and ask what exactly changed when our ancestors decided that nothing tasted quite as good as food touched by flame. So what did change when food met flame? Start with energy, because in biology, energy is always the quiet accountant in the back of the room. Cooked food is easier to chew, easier to digest, and often safer. Heat unwinds long chains of starch, softens tough plant fibers, and denatures proteins. It kills many parasites and pathogens that would happily turn your dinner into disease. For a hungry primate with limited daylight and a busy schedule of not being eaten, this matters. If you can get more calories faster, with less wear on your teeth and gut, that frees up resources. You can afford a slightly smaller digestive tract, slightly weaker jaws, slightly less time spent chewing. You might be able to support a larger brain, which is famously energy-hungry tissue. This is the heart of the cooking hypothesis, that regular use of fire to prepare food helped power the expansion of the human brain and the shift to a more gracile, less ape-like body. There is decent support for parts of this story compared to other primates. Humans have smaller guts relative to body size, weaker chewing muscles, and dentitions that look poorly suited to the kind of raw, fibrous diets gorillas or chimpanzees handle with ease. Experimental work shows that cooked and processed foods yield more usable energy than raw ones. All of that points in the same direction, but the timing is messy, and here the consensus softens. Large brains begin to appear in our lineage before the earliest uncontested hearths. Some researchers argue that heavy processing, pounding, slicing, grinding, could already have been boosting energy returns long before habitual cooking. Others suggest that early humans may have had access to unusually rich raw diets, marrow, brains, fat and soft organ meats, scavenged or hunted from large animals, nutrient-dense shellfish along coasts and rivers. Fermentation offers another possible pathway. Even without fire, leaving food to ferment can pre-digest starches and fibers, increase vitamin availability, and help preserve calories. There are hints that some prehistoric groups relied heavily on fermented or otherwise microbially transformed foods, although solid evidence is sparse. So instead of one magic switch, many anthropologists now see cooking as a multiplier. It doesn't create our trajectory from nothing. It takes trends that are already forming, better tools, more strategic hunting and gathering, more cooperation, more mobility, and amplifies them. If you're already making sharp stone tools to slice flesh, cooking makes those tools even more valuable. Roasted meat falls apart differently than raw, and you can process carcasses more completely. If your group is already coordinating hunts, fire lets you preserve surpluses, turning a lucky kill into days of security. If you're already exploring new environments, cooking lets you unlock previously marginal foods, roots, tubers, bitter plants that become edible once softened or detoxified by heat. Fire stretches time and space. A cooked meal can be shared hours after the hunt or carried days along a migration route. A hearth becomes a predictable centre point in a shifting landscape. Around it, social life thickens. Here the consensus is strongest. Whatever else cooking did, it clearly transformed how people spent their evenings. A controlled fire throws a small circle of safety into the night. Predators hesitate. Insects disperse. Within that circle, people can sit, talk, teach, and remember. Children can watch adults work and tell stories. Skills that once had to be learned in the heat of the day, tracking, tool-making, plant lore, can now be rehearsed in the relative calm of firelight. Language, myth, and technical instruction all find an easy stage in this new schedule. Even if language itself predates regular cooking, the rhythm of a day with a shared evening meal gives those abilities a place to grow. Stories can be repeated, refined, passed on. Knowledge survives individual lifetimes more easily when it has a nightly performance. Technology too takes a step change with heat. Once you're comfortable tending coals and judging temperatures, you can do more than roast meat. You can harden wooden spear tips, improve the flaking quality of some stones, experiment with clays that eventually become ceramics, resins that become adhesives, fibers that become stronger when smoked or dried, just so. In this view, cooking is less the star of the show and more the backstage crew, quietly making every other act easier to perform. It's not without costs. Anyone who has cooked over open flame knows how easy it is to burn yourself. Archaeological skeletons show traumatic injuries that might be from falls into fires. Long-term exposure to smoke in poorly ventilated spaces damages lungs, eyes, and cardiovascular systems. Today, indoor cooking fires remain a major health hazard. There is no reason to think they were harmless in the past. Dependence on fuel also ties people to certain landscapes. Wood, dung, peat, or other combustibles have to be gathered, stored, defended. In open environments with scarce fuel, the desire to cook might shape where groups settle, how often they move, and what kind of vegetation they tolerate or encourage. Fire can clear brush, but it can also strip a place bare if used carelessly. All of these threads lead to a pair of lingering questions that keep archaeologists and anthropologists arguing, softly, over their own metaphorical campfires. When did habitual cooking, day in day out reliance on heat-prepared food become normal for our ancestors? And why at that particular time? Someplace the turning point very deep in the past, over 1 million years ago, tying it to early Homo erectus and the first major leaps in body and brain size. Others think regular, near universal cooking may be much more recent, spreading gradually with certain technologies, durable hearths, pottery, agriculture, and becoming truly inescapable only when grains and other plants that almost require cooking dominated the diet. It's possible that different regions followed different timelines. Some groups may have lived for long periods on largely raw animal foods and minimally processed plants, using fire mostly for warmth, light, and occasional roasting. Others, especially where tough roots or toxic seeds were plentiful, may have leaned heavily on cooking from an early stage. Over tens of thousands of years, as populations mixed and climates shifted, the habit may simply have become so advantageous that non-cooking groups vanished or were absorbed. What we can say with cautious confidence is that by the time history begins to write itself in clay tablets and carved stone, cooking is already there, taken for granted. Every known civilization assumes the hearth, the oven, the pot. And yet, beneath all the debates about dates and causes, something quieter endures. Somewhere in the deep past, a group of our ancestors settled down at the edge of the dark with food that had been changed by fire, softened, warmed, scented with smoke. They shared it, argued over it, maybe laughed. They taught children how to tend the flames, how to know when a root was done, when meat had gone from dangerous to safe. Tonight, when you think about dinner, or remember the comfort of a favourite warm meal, you're touching that same thread. However the exact story unfolded, the habit of gathering around heat and food is one of the most stable constants in our tangled, wandering history. In a moment, we'll follow that thread back to the present and sit once more by the hearth, not just as a piece of archaeology, but as a place you still carry inside you. So after all this, what can we really say about why humans started cooking? Not with slogans, but with the kind of careful answer that survives daylight. The safest place to stand is here. Once our ancestors learned to control fire, using it on food became one of the most reliable ways to squeeze more safety and energy out of the world and to knit their scattered lives together. It wasn't the only change that shaped us, and it may not have been the very first. But the best evidence points to cooking as a powerful amplifier of everything that was already nudging us toward being human. Fire control came first. The slow, unreliable, repeatedly rediscovered art of keeping a flame alive when nature would rather drown it, scatter it, or blow it out. From opportunistic sparks, lightning strikes, natural wildfires, to tended embers, to hearths built in the same spot again and again. Then food transformation, roots that went from inedible to nourishing, meat that went from risky to safer, grains that turned from hard shards into porridges and breads. Each step changing not just what could be eaten, but how much effort it took, how far it could travel, how long it could last. Around these pools of warmth, social gathering thickened. Small circles of light in vast, dangerous nights, shared meals, shared stories, shared rules. Trust negotiated over cooked food, secrets passed down in whispers over glowing coals, and from that, innovation. The confidence to experiment with heat, to harden wood, to temper stone, to fire clay, to smoke fibres and seeds and meats. The patience to sit and watch something transform slowly, and to remember the steps well enough to do it again. Those are the through lines: fire, food, people and ideas braided together over hundreds of thousands of years. But the exact order, the precise dates, the moment when sometimes cooked became always cooked, those remain soft-edged. Some questions may never sharpen. Sediments erode, bones crumble, ash scatters. Our picture of deep time is stitched from fragments and probabilities, not perfect records. That uncertainty isn't a flaw, it's part of the story. It reminds us that the past is not a fixed script, but a gradually improving guess. New digs, new methods, new ways of reading old evidence can still surprise us, and probably will. For now, you and I are here, at the quiet end of that very long day. Somewhere, far behind you, an ancestor is feeding a fire with whatever fuel they could find: twigs, dung, driftwood. Someone else is stirring a pot, turning a spit, or just lifting a charred root from the coals, testing it with cautious fingers. Children are slowing down, voices are dropping. Outside the circle, the night presses close. And then, jump forward, to you, wherever you are listening from. A city apartment with traffic humming far below, a farmhouse with crickets outside the window, a dorm room, a ship's cabin, a quiet corner of a crowded house. Maybe it's late at night, maybe it's early morning. Maybe you're dozing, halfway between here and sleep. If you'd like, you can let that ancient circle and your own space overlap for a moment. The warmth of all those past fires folded gently into the warmth of your bed, your blanket, your breath. Before you drift off, if you're still awake enough, I'd love to know where you're listening from and what time it is for you right now. You can leave a comment: small town, 11:42 p.m, or big city, just after dawn. It's a simple way of turning this into a shared hearth for a moment, tiny lights scattered across the map. If this slow walk through the history of cooking helped you relax, or gave you something gentle to think about, you can also tap like, leave a comment, or subscribe, so you can find your way back here next time. No pressure, no rush, just an open invitation to return when you want another quiet story. For now, you don't need to solve any mysteries of human evolution. The debates can wait, the timelines can blur, you can let your thoughts bank down like coals at the end of the night, glowing softly under a layer of ash. Breath in, breath out. The long history of fires and meals and shared nights is already inside you. If sleep is coming, you can follow it. And if you're staying awake a little longer, you're welcome to linger by this hearth or wander on to the next story, carrying a small, steady flame with you into the dark.